Okay, so welcome. This is the week 6 webinar. So we're at the halfway point. So hopefully that makes you feel good. You know, we're just right there because it's a 12-week class and this is the week 6 webinar. So we're right at the halfway point. And the nice thing is we've done a lot of the prep to be able to use statistics. And from now on, everything we do is like super useful. Okay. And not like this theorem and that theorem and, you know, a bunch of formulas. It's just using statistics. And that's what today and the rest of the quarter is going to be, is using statistics for important stuff. I will have no problem for the entire rest of the quarter going online, finding a recent article and showing how it uses statistics, because what we're doing from now on is used every week. So that's the good news, and not some weird field. So hopefully you'll see it. You might think it's weird, but I don't think you'll think this one's weird today, and most of them won't be. So let me share my screen and talk about the plan. Okay, so you should be able to see it. Oh, let me make sure I can look at chat. There it is. Just want to make sure I can see the chat board. And the plan today is we'll start out with Q&A. So I'll answer any questions you might have. It probably won't be on the project other than when is it going to be graded? And I've graded some already, but I can't grade it. It's a lot of pages. I can't just grade them all in one day. So hopefully tomorrow I'll finish them. Some of them I graded already today. So as you might have noticed, I'm not a procrastinator. So, you know, I don't wait. And I wanted to make sure your discussion posts were graded. That was 4 in the morning this morning. Yeah. So, so we're going to do Q&A. So if you have questions, I'll be happy to answer. Project 2, just let you know, it's a little early to even think about. I mean, you, other than maybe your partner, but we don't have the information yet. Next week, we can start talking about it. We're going to get into confidence intervals for means. So that turns out to be a very important thing that's used all the time in any kind of research, even basic research, not some kind of hardcore science stuff, but just basics. Every field uses confidence intervals. And I wrote means, but also proportions. So very important to be able to say, well, you know, we did our study and we found out that this % of the population said something, but you don't know about the population. You only know about the sample. So you got to be careful about saying this % of the population. You know, this % of your sample said something. But now the question is, how reliable is that? So even if you have no bias, if you have a sample of size 100 and there's 350 or so million people in America, you have this little tiny group. And the question is, how good is that sample? And we'll talk about that. And we'll say, how confident are we that the population mean is close to the sample mean? And it has everything to do with the central limit theorem.
Man, I've been wondering that since we started this class.
Today's a big day in terms of that. Last week was the big week in terms of getting the math ready to be able to do what we're doing today and doing what we're doing next week. Okay. And then after that, we're just going to do variations of what we're doing today and next week. And today is about confidence intervals. Yeah. So if you're wondering about since the start, I know it's been 6 weeks, but we're there. So everything we do is like, just makes sense. Lots of great applications. Okay, the other thing, and we talked about that you had to have over 30 to be able to use a normal distribution, right? But that's just to use a normal distribution. But the problem is your standard error going to be small enough? Because if the standard error is really big, then your sample mean may be really far from the population mean, because the standard error being big means that it's pretty likely that you're far away. Whereas the standard error is small, then it's pretty likely you're close to the population mean. And the standard error, if you remember, in the formula had a square root of n in the denominator. So a big question is, if you want, let's say you wanted to know, I don't know, let's say you wanted to know income of college graduates, first year income. Well, you could survey 100 people and you're going to find their average income. And if you have an unbiased sample, it sounds good, but are you going to be off by too much? Like maybe your sample size is too small. You could survey 50,000 people. That's a much bigger sample size, but that's really hard. I mean, for the project, it was hard enough to get over 30, like to do 32. 50,000, good luck. So the question is, how many people do you need to survey so that you have results that are comfortable with what you need? Does that make sense? And we'll get into the details later, of course, today. And we'll also look at sample size for proportion. So same thing, how many people do you need to survey so that you're going to be able to say with good confidence that here's the proportion and I'm not off by much. Does that make sense?
Mhm.
Yeah.
You know, but if you said, you know, hey, I did a sample and I found out in my sample, let's say, you know, 70% of Americans are really upset with Russia right now, but I might be off by 90%, then you have a ridiculously stupid sample, right? Do you see how that is?
Mhm.
But if you're only off by 1%, then your sample's probably pretty, that means that you're really comfortable and that's good. And you've got a big enough sample size. So we're going to be looking at what sample size you need so that you can have comfortable results. Does that make sense?
Mhm.
Yep.
And I'm going to let you know that all of this has a lot of brutal mathematics. Why should you be happy?
Calculator.
Later.
Yep, if it's brutal, that means you get to use a calculator. Okay, if it's pretty easy, that means you have to do it. So the good news for you guys is it's brutal, which meant I had to do it. But that you can trust me, that's my field. So that is the plan of the day. And I want to remind you, this is week 6. 6 is an even number. Why am I reminding you that it's an even number?
Exam.
Yep. So remember, at the end of every even week, you have to have your exam taken. So exam, the third exam, the week 6 exam has to be done by the end of Sunday evening. Okay. And you might as well do it on Saturday or something, you know, no reason to wait till the very last minute. So that's just a note, very important to make sure that, you know, you're all ready. So any questions about anything? Great time to ask.
For the exam, it'll be 50% this week and last week and 50% all previous weeks.
Yeah, approximately.
Okay.
Like it might be 55% or 45%, but yeah, basically, yeah. So and that's kind of how I've done it. That way you're always tested on prior stuff, but there's a big focus on the new stuff. Hopefully you're okay with that. Again, I'm just making it up as I go. I don't know anyone else has tried this, but it seems to work. Again, this is my second quarter. So everyone is happy about it last quarter.
I like it. I like it a lot better.
Yeah, because again, what I used to do is have a midterm and a final, and that was it. And you had to go pay someone to proctor the midterm. It was in person. Or you can go to our college, except our college doesn't do that anymore, which kind of sucks. Our public library charges.
Mm.
So I'm like, no, and hopefully you get it. I'm not into making you pay money for this class. Yeah, I guess you have to pay the electric bill to have your internet on right now and your internet bill, but that usually people don't complain too much about. And if you're in Tahoe right now, actually, that's nothing compared to the heating bill tonight. Any of you in Tahoe?
Mm.
We got a load of snow today.
Oh, wait.
Yeah, it's all white outside. Yeah, so I try not to make you guys pay for the class.
It was snowing down in Reno too.
Reno, really? Wow.
Yeah, I live in Reno, so
Wow, that's a lot lower than here. So yeah, so you got to pay for your electric. You got to pay for heating. No way out of that one. So any other questions? Okay, if there's no questions for you, I'm going to ask you a question, and we don't have many of you, which, oh well, I think I'll answer it too, because if we only have 4 of us, we got to do what we can do. I always rather have everyone show up, but I can't make that happen. So here is the question. It's one of my favorite, and I've been asking this literally for over 25 years, and I've watched it change.
Really?
Oh yeah. How old were you when you experienced your first passionate kiss? By the way, when you were 1 year old and your mom kissed you on your cheek, that's not passionate. That's lovingly by a relative. There's a difference.
Mm.
So that's the old boyfriend, girlfriend kind of thing, that kind of passionate kiss. And the rule is you have to put something in the chat box. If you feel uncomfortable, make something up that's reasonable. Don't say 99 years old, because I know you're not 99. And you have to put something in, all of you. Okay, and I'll put mine in. Look at that. Wow. Perfect. So by the way, what distribution is this?
It is a right. No, it's a uniform distribution.
Yeah, there's a uniform distribution, because we're all like one away from each other exactly, and there's exactly one of each. Okay. I've never had that happen before, by the way, but you never know. Okay. So let's write this out. So we had 15, 14, 12, and 13. Okay. Now, sorry, 13. So first thing, I want to give you a big heads up. Sample size is way too small to do anything. But there are times when you have no choice. Why do I have no choice?
There's nobody else here.
Yeah, exactly. We're a small group today. So normally I have more and we have a bigger sample size, but we can still do it. Okay. So we have a sample size of 4. We got a major assumption that it's normally distributed, right? Because if it's not normally distributed, you can't do anything. Again, it looks uniform, but we don't know.
Uniformly distributed though.
Yeah,
right?
but we don't know the whole population is uniformly distributed. And what we're trying to do is represent, let's call college people, since I answered. Otherwise, there'll only be 3 data points. So I'm a college person. I'm not a student. Okay. I was a student. I've taken a few classes here at LTCC, but they're like kayaking and stuff. So we have these, and because we have these, we can actually do some calculations. And the nice thing is I can remember these. I don't even have to actually like go back and forth. It's 12, 13, 14, 15. So I can go to the calculator. I can go to my one variable stats calculator. And I can go to 12, 13. I don't remember the order, doesn't matter. 14, 15. This is a sample. And hit calculate. Okay, so just to note that 13.5 is a mean. What kind of mean is this? Is it a population mean, is it a sample mean, or a mean as a sampling distribution?
It's a sample mean.
It's a sample mean, exactly, because it's the mean of this sample. So that means it's an X bar. So it is important you get the letters right. Again, I know it's a review from last week, but we're using last week's to do this week. So 13.5 is our X bar. So I'm going to put that in. Our sample standard deviation, that's why I clicked on sample standard deviation, is 1.291. How about our, oh, this is a cool one. I can actually do this one in my head. how do I get our standard error?
You divide 1.291 by the square root of 4. No.
Yeah.
Yeah.
And the wonderful thing is the square root of 4, I think you can all do in your head.
2.
Mm-hmm. 1.291 divided by, I'm just going to write root so I don't have to make it fancy, of 4. And by the way, that we can do because that's just divided by 2, which is 0.64645. See if I did it right. Oh, not 64. Let's see. Nope. 0.6
0.6455.
55. Yep. 55. Off by a little bit. There we go. So there's our standard error. Okay. And remember, the standard error is the standard deviation of the sampling distribution. And in this case, it's sample size of 4. Any questions on that? Is that clear so far? Okay, so now what we're going to do, and we're making this big assumption that the distribution of the population is normal. Why do I have to assume the population distribution is normal?
Because it's not greater than 30.
Right. We're looking at a sample size of 4. So it's not even marginally close to 30. So we have to make a big assumption that the standard deviation is, the sampling distribution is normal. Does that make sense? All right. By the way, what are the first 3 letters of the word assume?
Ask.
Exactly. And the next ones are you and me. So making an assumption is making an ass of you and me, just let you know that. So it's never good to have to make an assumption. Is that clear? Which is why you always want a sample of size greater than 30, because then you don't have to make an ass of you and me. Got it? It's a good way to remember it. Okay. Okay. And that's when we're talking about means. All right. But we're going to make that assumption. So here's what we want to do. And this is standard. Let's use the standard level of confidence. Okay. And that may not mean anything to you yet, but by the end of this webinar, that's what this webinar is all about, is confidence intervals. So the idea here is you want to say, well, I can't say that the population mean age of first kiss is exactly 13.5. That's just wrong. Okay. Because this is an X bar. It's not a mu. Is that clear?
Yep.
But our standard error is a little more than a half or so, right? And we've learned that if you take 2 standard deviations away from that mean, how much of the data stays in that interval? Do you remember?
95.
Yep, 95%. 95%, okay, of the data stays within 2 standard deviations of the mean. Any questions on that? So what is that? Any questions?
No.
Okay, so what we can do is we can double this. We can say, well, within 2 standard deviations, that means we're going to double our standard error. And we're going to go left and right, double the standard error. Okay, one of the great things about this particular example, we happen to have a root 4, total coincidence, by the way. So I could do this without any work. If I take double 0.6455, I happen to get 1.291. By the way, that's a coincidence. That's not going to happen in any other situation because you're not going to get sample sizes of 4. But in this case, that works. So what I can do now is say that if I take my X bar 13.5 and I subtract double, I'm going to write 2 times 0.6455, then what do I get? I get 12.2 or so.
$12.20.
Wait, sorry. Yeah, 12.2 is good enough. Honestly, does anyone really care whether the average age of first kiss would be, say, 12.2 or 12.21? No, no. You care about your own first kiss because everyone remembers that day, right? I remember my day. But in terms of an average, 1 decimal place is just fine, don't you think? And you want to think about that into the real world. How many decimal places do you really need to have good data? And in this case, I think 1 decimal place, don't you all agree, that's good enough for if you wanted to have a good guess on the average age of first kiss?
Yes.
Yeah. Okay. So I'm going to use 1 decimal place. And if I take 13.5 and I add twice the standard error, 0.6455, then what I'm going to get is 14.8. Any questions on that?
No,
Okay, this is a big deal, by the way. Okay, this is kind of what we're doing. There's going to be modifications we're going to have to do for math reasons, but this is the idea of confidence intervals. So now, at least as an idea, we can say with 95% confidence, the population mean age of first kiss is between 12.2 and 14.8 years old. So I want you all to look at this because it's very important. So a couple things, whenever I ask you to state your results, then the first word should be with. Not too hard to remember. First word should be with. And 95% is the most commonly used level of confidence, not just because it's a nice number, but the reason happened about, I think it was around 90 years ago. And that was, there was actually a political thing, political survey that happened. And there were 2 groups. One group used 95% level, and another group only used 90%. And the group that was 90% didn't do as well. It turned out they were wrong. And the group that won pretty much convinced everyone. And the group that won, see if you know who was the most important news 90 years ago. None of us were born yet.
Donald Trump.
90 years ago? He's not that old.
I
I don't mean
I
person.
thought you said 9. Sorry.
is
No,
it,
90.
Nine years ago.
is it
90
Dewey
years ago.
versus Truman?
Yeah, but not person. Agency, news agency. Anyone know?
ABC,
Huh?
CBS.
Good try. Television didn't exist. That was before television had even been invented yet. All
New
right, I'll
York
tell you.
Times.
Yep, New York Times. So the New York Times, actually, they are the ones that decided that it would be 95%. And it was based on this big election. And since then, we've all used it. Okay. It is used not in every situation, but I'll let you know it's used in all political science. It's used in just about all of social sciences. That's like psychology or in sociology. But it's not used in everything. When I think I've mentioned I did some consulting work for the Forest Service. And, the boss is always right. You know that word, that saying, right? And the boss said, we're doing 90%. And I need to explain what it meant just to make sure they understood statistics well enough. And they said, no, we're doing 90%. So just because most do 95, sometimes you'll see a 90%. Sometimes you'll see 99% or 99.9%.
Do you have to have a normal distribution in order to be able to make that call?
So here's the key. In the situation that we just did, the answer is yes. And how come?
Because we assumed that it was normal.
Yeah, that big old ass of you and me. And that we had to assume because our sample size was 4. As soon as your sample size is over 30 for a mean, you don't need any assumptions. Okay. The only thing you have to make sure of is you have an unbiased sampling. If you have biased sampling, you can't do anything.
But isn't that only for sampling distributions, not for just the sample? Do we
Right,
only
but-
learn-
Check it out. SE.
Gotcha.
There. Yep. Talking sampling distributions. So this confidence interval used the sampling distribution to do the computation. Any questions on that? Okay, so by the way, again, our sample size is so small, it doesn't, it's not going to show up. But when I first taught the class versus now, age of first kiss, any guess on what the change has been?
Lower? Lower and lower?
One more guess.
3 years.
Yeah, higher. Yeah, age of first kiss has gotten much older in the last 25 years.
Really?
Absolutely. And not only that, and I'm on YouTube, but I think I could say it anyway, not just kissing, but you can go to the next much higher level up from kissing, which is
Having sex. Is it because of
Sex.
social media?
sex and having babies.
Wait, it's gone up, not down?
Oh, way up. Yep. Yeah, way up.
Wait, so kids used to have their first kiss at 8 or 9 or something?
They used to have their first kiss at 11 or 12. I was like such an old guy. I was 13.
Wow,
All my friends
honestly,
were
I thought it would have gone the other way.
No.
but-
No, it didn't. It didn't. And age of first child has gone way up. Just like
Yeah, I could picture that. That makes sense.
Yeah, so it's all gone up, just let you know. And again, I know that from my own, doing this, but I also know it from reading too, because I read statistics whenever I can. And I look at data and I remember it. So it's not just all my students, but I've seen it nationally and internationally too. Okay, so let me just
How
show
many
you.
kids people are having is going down too. Wait,
What's that?
how many children people are having?
Right, but the main reason for that is they're starting late.
Right. Okay, that makes sense. Yeah.
If you don't start till you're 35, you're probably not going to have as many children as someone who started when they're 18.
Yeah. Good point.
Yeah, so that's definitely, there's all kinds of statistics on that. It's all stats, and I always follow the stats. Okay, after the lecture, I can talk to you some real deep stuff about war and that kind of stuff. It's all has to do with that, or not all, but a lot. So here's a picture. It's what we just did. Hopefully you recognize it. Okay, in a word, what is the shape of this picture?
Normal.
It's a normal distribution. And either you have to assume, but hopefully you never have to assume, because in the real world, you always have a large enough sample size. You just do it. You do the right thing. So you have a normal distribution for the sampling distribution. And the way it works is if you have, let's say instead of a 95% level of confidence, let's say your confidence level was, let's say 80%, just to make the math in our head a little easier. So that would mean that in this shaded area, that area is 0.8. Any questions on that? So if the area inside is 0.8, then the area total outside is 0.2. Got it? But then you have to divide that by 2 to get the area to the left. And that's 0.1. So that's what these letters are. So the idea is 1 minus 0.2 was 0.8. So whichever side you want to call the 1 minus. And then divide by 2, that's the over 2. So if you have an X bar in the middle, then you go left and right by E. Any guess what E stands for? It's not some fancy statistics word, by the way. You all know this word. And you've known it since you're...
Extra?
Good try.
The error?
Error. Yeah, it's the error. Because your guess is X bar, but then there's an error. And you're going to say that the error that you're going to call most likely is somewhere between, is E on both left and right. And that's why you go left by E, that means X bar minus E. And you go right by E, that's X bar plus E, which is what we did in this example. Any questions on that? Is that clear? So that's the general picture. There's some issues and there's stuff we have to do. And here's a big issue. So the central limit theorem, hopefully you remember, I told you it was the most important formula, and that is sigma sub X bar was equal to sigma over root n. Isn't that what we did? Did we take sigma and divide by root n?
Yes.
The answer is no. How come?
Because we didn't really have root n. We just had the sample size.
Actually, we knew root
The
n.
standard deviation, we use the sample standard deviation, not the population.
That's the problem. So we did have n. N was 4. Root n was root 4, which is 2. So that we had. That's no problem. But what we didn't have was sigma. And that sigma is you'll never have. You will never know sigma. Is that clear? Because to know sigma, you have to know the entire population. But if you know the entire population, then you know the population mean, and you don't need to do any of this stuff because you know it for sure. Any questions on that? So it turns out everyone used to just do what we did, which is use this formula until around 100 years ago or so. And believe it or not, it had everything to do with beer. And that's what you're all thinking, right? You want to guess why it had everything to do with beer?
Alcohol content?
Something like that. There was a professor of statistics who had 2 jobs. One job was to teach statistics, and the other job was he worked in a brewery. And he actually figured out that he wasn't getting it 95% of the time right. And that's what you want. He was getting it right less often. Okay. So he did a lot of math and he came up with a new distribution that I can't even get close to explaining. It doesn't look that much different than the normal distribution. But if you go to the book, by the way, I programmed a little slider that shows how close it is depending on the sample size. A bigger sample size, you get it closer to normal, it turns out. No, I mean, closer to the population. Standard deviation and sample standard deviation should be closer to each other. And you get to see the special distribution that deals with the fact that you don't know sigma. And the guy who developed it, he named it after his students. And he called it the student's t-distribution. So we're going to be using what's called the student's t-distribution to be able to handle this. And that builds in the extra error in using the sample standard deviation, because you can't know this population standard deviation. Any questions on that idea? And the math is way too hard. It's not even undergraduate math, it's graduate level math, just to let you know. So even Braulio, you don't know this math, right, Braulio?
No,
Yeah.
I can't say I do.
Yeah, the math is really brutal, but it's cool if you're a mathematician like me. So just let you know, we're not going to use the normal distribution. We're going to use an approximation of the normal distribution, which is called the t-distribution. Okay. But again, the good news is, since it's so hard, you don't have to worry about it. You just let the calculator do it. Sound good? Okay. But what I do want you to know is the letter T. That I can ask you to do, right? I think that's fair. Okay, so you're going to learn about, you're going to use the t-distribution in coming up with this. All right, so interpret the confidence interval. I already did. That was up here. Where is it? That was this with 95% confidence. The population mean age of first kiss is between 12.2 and 14.8 years old. So let's put that back in so I can answer it. So any questions on interpret the confidence interval? And I bold-faced it, but I think I'm going to do even more because so many people have trouble with this. So let me, where is it? I want to make it red. So you just see that that's a very important thing. So if you want to interpret the confidence interval, then it starts with the word with. Got it? All right. What does it mean to be 95% confident? Any thoughts? All right, because we did it in the calculation. Is we use that 95% confidence, right? If it was a different confidence, then you wouldn't have this 2 here. You'd have something else. So in the picture, if we wanted it to be, say, 99%, then this shaded area would have to be a lot more of it. And we'd have to go farther left on this left side, and we have to go farther right on the right side. Do you see that? So what does it mean to be 95% confident? Any thoughts?
95% of the answers fall within this range.
Really good idea. But
What
my
about,
guess is your thinking of the word answer is different than my thinking of the word answer. So I'm gonna go with what you said, but I'm gonna change the definition of answer. Sound good? Another thought?
the probability that the first kiss is between 12.2 and 14.8 is 95%?
That's a good idea too.
It's like your 95%, there's a 95% chance that the population mean is between 12.2 and 14.8.
That's a good way of thinking too. But I want to let you know that the word chance and the word probability are hard to even understand. What does it mean to have it be a chance or a probability? Does that make sense? So let me explain in a story. Okay, or maybe a imagine a scenario. So here's a scenario. And the scenario is your job is to write news articles, do research, and then write articles about your research. Got it? That's your job. So let's say every day you write another research article. In other words, you conduct another study and you get a confidence interval. And each day you publish a new one. Does that make sense? Then the problem is that with this standard error, some of the time you're going to publish that the average age of first kiss, for example, is between 12.2 and 4.8 years old. But it could happen that you got unlucky. And you just happen to ask a bunch of people that maybe kissed young when the real average age is out here somewhere. Do you see that? So what you can think about is, let's say you did your job 100 times. So 100 different times you surveyed 4 people. And so every day you did that for 100 different days. Each day that you do that survey, you're going to have different answers. You're not always going to have 15, 12, 14, and 13, right? Right? It just all depends who you ask. Even if it's unbiased, you're asking 4 random people, adults, right? And some of those days, your sample mean and your confidence interval will actually contain the population mean. It'll be somewhere in here. But some of the days you're going to have a different confidence interval where the population mean is not in your interval. Do you see that? Sometimes you're going to get lucky. Sometimes you're not going to get lucky because there is luck involved. And that's kind of what chance is, or probability. It turns out that 95% of all of the possible confidence intervals that you could ever do are going to be the good ones. They're going to actually contain that population mean. And 5% are going to be awful, which means you blew it, and the population mean might be over here or it might be over here. And it didn't contain it. Do you see that?
Does the sample size matter?
So the sample size matters in how wide your confidence interval is. But the 95%, the fact that you're 95% has nothing to do with the confidence interval. Does that make sense?
Okay.
So if your sample size was, say, 1,000 instead of 4, you would still end up with a 95% confidence interval. But then your, what we call margin of error, this E, so that's how far you've decided that you're going to be able to cite your evidence. That's going to be a very small E. So then you might end up saying that, you know, with 95% confidence, I know that the average age of first kiss might be between, instead of 12.2 and 14.8, you might be able to say is between 13.002 and 13.003. Do you see how that works?
Okay.
So you're like right on. And but there's still a 5% chance that it isn't in that interval. It might be, say, 13.4. Do you see? But it's not going to be, you know, 12.1. If you have a giant sample size, you're going to be really close. Do you see how that works?
Yeah.
So you want to decide it's a give and take kind of thing, is that you can choose your confidence level. So if you choose your confidence level to be, say, 99%, then your margin of error is going to be much wider. So I can be 99.999% confident that the average age of first kiss is somewhere between 0 years old and 140 years old. Do you agree I'm that confident? Do you trust me?
Yeah.
But have I given you any information that is any at all useful to yourselves?
No.
No, because I told you the average age of first kiss is between 0 years old and 140 years old. It's worthless. Do you see that?
Yeah.
So it's a give and take. If you want to be much, much more confident, then you're going to have to widen your margin of error. Do you see that? If you're going to be less confident, so I could be 2% confident that the average age of first kiss is like between, you know, what was our sample mean? 13.1 and 13.4 and 13.6. Sounds great because I'm right on the spot, right? But I'm only 2% confident. That means that 98% of the time I'm wrong. Do you see that? So do you see the give and take?
Yeah.
But
So the only-
the larger your sample size, the tighter your margins can get.
Right. So the only way to have both of the good things that you want is to, as you said, raise the sample size. Right. So if you raise the sample size by a factor of 100, you're going to decrease the margin of error by by 10. Or you can say, well, we're going to raise it by 100. We're going to not decrease by 10. Maybe we're going to decrease by only 5, and we're going to be 99% confident. Do you see that? So it's a give and take. Okay, but what's the problem with doing a sample size of 1,000?
It's very difficult to get that many people.
Exactly. I'm going to tell you that in the real world, it's very expensive.
Yeah,
'Cause
expensive too.
you're not going to do it yourself. You're going to pay people. You're going to hire people to do it. And I don't know if I mentioned it. Did I tell you what my first company job was?
No.
I was that guy who called people on the phone and asked survey questions. Okay. Now, like, you know, I'm old. Any guess on how old I was when I did that?
20?
I was 11. Life was different in those days. Children worked. Yeah, and that was my first job. Nothing to do with me being a statistician. I was 11 years old. I was just a kid. But we needed the money. Family needed money. So just let you know that I actually have the experience of surveying people. I did it as a kid in a company called Carroll Davis Market Research. It's kind of cool. So I know like firsthand how much work it is to ask a lot of people. Okay. And it wasn't cell phones in those days. They didn't exist. Okay. Any questions on this confidence interval idea? Okay. So the next thing is, what does it mean to be 95% confident? So let me put it in words since we just talked about it. This is a lot of people have a lot of trouble with this. So, you know, pay attention and see the difference between the confidence level and the confidence interval. In fact, I'm going to red highlight level to focus that it's not interval, it's level. Any questions on that idea? Okay, so with the confidence level, again, we're looking at being in the profession of doing confidence intervals. So we can say if many samples of, in our case, it was size 4, were taken, then each of these samples will result in a different confidence interval. Right? So if I asked a different 4 people, I'm not going to get the same numbers, right? Yeah, different numbers. And those different numbers will give me a different interval. I'm going to get a different sample mean, and I'll get a different sample standard deviation. So I'll get a different sample. I'll get a different confidence interval. Is that clear? 95% of these confidence intervals will contain the true population mean, age, too many ups, of first kiss, actually passionate kiss. Okay, and 5% will be misleading because they won't contain it. I'm going to say I'm 95% confident that it's between these numbers, and guess what? It wasn't between those numbers. 5% chance, 5% of the time. Any questions on this? There's no short way of writing it.
Why are you saying 95% of these confidence intervals will contain the true population mean instead of 95% of these confidence intervals will be between 12.2 and 14.8?
Because they won't be between 12.2 and 14.8.
I see, because
they're
the
going to be
population-
different. Some are going to be lower, some are going to be upper. None of them are going to be exactly the same, or very few, right? Do you see that?
Right, yeah, I understand that too.
Yeah.
And then this
And
says the population mean age is between, okay.
Right. And that's your goal. Your goal is to get the population age of first passionate kiss. And what
Right.
this says is 5% of the time your goal will be successful. And
Right.
I sorry, 95%. And
95,
5%
yeah.
will be unsuccessful. Do you see how that works?
Yeah, I got you, yep.
Yeah. So that's a good question.
Sampling distribution. It's very similar. right?
What's that?
It's kind of like a sampling distribution. You're taking like a whole bunch of,
Absolutely. This all comes from the central limit theorem. What we did last week was not a coincidence. Okay, it's completely related to this, as we saw in the calculation. Okay, so I just have some templates. And that is with, if I write XXX, don't write XXX, please, in terms of when you're doing it for, answering a question. But, it might be 95%, it might be 90%, it could be some whatever percent confidence. It can be concluded the population mean, XXXXX, in this case, it's age of first kiss, do you see? Is between whatever the two numbers are. Okay, notice it's not the sample mean, it's the population mean. That's very important. And then if many samples of however many, we had 4, but normally you'll have more, are taken, then each would produce its own confidence interval. Whatever percent, in this case 95%, of these confidence intervals will contain the true population mean. In our case, it's age of first kiss. And in this case, 5% won't contain the true population mean. Any questions on the templates? Okay, please do not put in XXX when you're doing it in like the discussion assignment or the written exam. Don't use XXXX. Put in context. Does that make sense?
Yes.
Okay. Now, a sample size of over 30 is still required if we do not know the population distribution is normal. That we talked about already. Okay. Let's get the real confidence interval, because again, I lied about this. These numbers aren't quite right. Why are these numbers aren't quite right in this calculation?
because we're not using students T.
Yeah, we're not using students T distribution. So let's do it with the students T distribution, which will be easy, I promise. Okay. What we do need to know is X bar. We need to know S, or we need to know 15, 12, 14, 13. I'm going to use those. They probably come up a little more often. So I'm going to go back to the calculator menu. And we have a confidence interval for a mean with statistics. That's when you know X bar and you know S. Or with data, and that's when we just have our data. So if we were just starting out, with doing this, I just copy and paste my data, put commas between. I want to let you know something, because this is a mistake some people make that I can't do much with. If you have a number like 15,1236, don't go 15, comma 236. Don't put a comma when you have large numbers, because commas are only to separate the numbers themselves. Got it? But that's a mistake some people make with the calculator, is they'll put a comma and then the computer will think that that's 2 different numbers. So don't use commas for large numbers. Just put commas between numbers. Does that make sense?
Yep.
And then if we want, say, 95%, again, in the directions, it says, for example, 95% confidence level, enter 0.95. Okay, and hopefully that wasn't too hard. Did it look hard?
Nope.
Yeah. There's the X bar, there's the S. Here's our lower bound. And it's really about 11.4. Here's our upper bound, which is about 15.6. Notice it's slightly different, and that's because of that student's T distribution. And by the way, when you only have a sample size of 4, you tend to be much more off than if you have a large sample size. Okay, so if you try to use Z with a sample size of 4, it's off by a bunch. Okay, if you have a sample size of 200, it's basically the same. Any questions at all on doing this with the calculator? Okay, so now I did one with you all. Now let's do a news article. All right, so here is the question. What percent of Americans think that it is a good time to buy a house? What do y'all think? What's your guess? Without looking into it.
0.
It's not 0. Remember that some people really need that house. And it's a good time for them because they
I
have
think
to
I
have it.
used this article for my last discussion. I think it was like 30 or something.
Mhm.
Okay,
Yeah,
30.
yeah, you might have used that one because that's right. It might have been used.
I'm
Sometimes
pretty sure I used this. Yeah.
Yeah, so you even know this one. Yep. Okay. And here it is. Now, if you read, you'll see the 30. I literally copied and pasted. This was Gallup. Record low in the United States says good time to buy a house. By the way, it's not 0%, but it's actually a record low. Okay. And I've been telling a lot of my friends this is a bad time to buy because I've looked at all the statistics, by the way, not just the people, but financially.
Wait,
Okay.
it's a good time to sell?
What's that?
Would you say it's a good time to sell?
If you're going to sell and not buy a bigger house, it's a great time to sell. But a couple weeks ago, it would have been probably better. But yeah, that's a great time to sell. Okay, now, yeah, might be wrong, but based on the math, it looks like a good time to sell. Okay, so 30% say it's a good time. Okay, and I'm going to keep it at that. Okay, and then to save you time, I copied and pasted a little bit. It's down 53 percentage points from a year, 23% from a year ago. That's huge. And it's the first time the figure has been below 50%. Okay. So notice results from this Gallup poll are based on telephone interviews conducted April 1st through 19th, 2022. So it's pretty recent. With a random sample of 1,018 adults, age 18 and older, living in all 50 US states and DC. And then it says for results based on the total sample of national adults, the margin of sampling error is plus or minus 4 percentage points at the 95% level. Okay, so just a note. In our picture, instead of X bar, what letter are we going to have for this example?
30%?
No, what letter, not number, what letter?
We're gonna have, is it mu? But it's not mu because it's not a population.
Okay, so let me ask you the question. I'm going to ask you the survey question. Do you think it's a good time to buy a house? Answer that question.
No,
Okay, did you say 22 or 18? No,
P
you
or
said
Q?
no.
P?
Yeah. So if you said no, that means it's a yes, no survey question. Got it? A lot of people have difficulty identifying yes, no survey questions versus quantitative survey questions. Whereas the when did you have your first passionate kiss? That's not yes or no. That was a number, right? 14 or 13. Okay. But this is a yes, no survey question. So we don't use X bar. It's not P. P is for the population proportion. And you remember the sample proportion? What letters?
P hat.
P hat.
P hat. Yeah, it's P hat. So it would be a P hat, not an X bar. We're going to still use E. Okay. And we're going to have a P hat minus E and a P hat plus E. Okay. I will tell you the original textbook, the OpenStax textbook, did not use E for any of this stuff. It was so damn confusing that any guess on what I did?
Wrote a new textbook.
Not quite. but I modified the textbook that was written. And the great thing about these, what's called OER, Open Educational Resources, which we're using, not only that it's free, but I can make changes. And it just drove me crazy, the stupid letters they were using. So I changed it to all E. So when you read the book, it's all E. But if you go to the original OpenStax book, it won't be E. It'll be confusing as hell. Just trust me. So, and all the faculty agreed with me, not just at my college, but in lots of colleges, that E is better. So E stands for error. So we're going to be looking at P hat minus E and P hat plus E, and that will be where we're going. E is the margin of error, which they said is plus or minus 4%. Is that clear?
Yep.
Okay. Let's see if they were right. Good idea. Okay. How do we see if they're right? Any guess? How are we going to calculate it?
You can run it through the calculator.
Yeah, we'll go to a calculator, but it's not going to be the same calculator because this was a calculator for means, remember? So it's very important that you know which calculator to go to. So I hope you can all tell me which one I need to go to.
12.
Well,
Yeah, 12, confidence interval proportion. So always ask yourself the survey question. And if your answer to the survey question is yes or no, then you use proportions like number 12. If the answer to the survey question is say 14, then you're going to be using means. Got it? Okay, N was 1,018. Don't put a comma in. 1018. That's why I spent time saying don't use commas, even though the article used commas, don't use a comma. X we're going to do a little work on because we were told 30%. That was in here. 30% said it's a good time. So we need to actually find 30% of 1,018. But the good news is I can click scientific calculator. I can go 0.30 times 1018. Okay. By the way, was X 305.4?
No, you can't have 0.4 of a person.
Exactly. Can't have 0.4 of a person say yes. So do rounding, make it 305. Got it? So X is 305. Confidence level, they actually told we're going to use the 95%. So that was here. Here we go. So 95%. And one reason I like Gallup is they actually say the confidence level. But other places do too. And now I hit calculate. Okay. By the way, the P hat is 30%. We already knew that because that's what we did. But the upper and lower bound is, say, if you turn these into percentages, it's 27.1% to 32.8%. $32.8 was it? 32.8. And I'm just rounding to the one decimal place, which is no one cares about like 1/100 of a percent on something like this, right? Okay. By the way, the margin of error, let's figure it out. That is going to be 32.8% minus 27.1%. But if we look at the picture, that would give you here to here. Do you see that? But that's twice the margin of error because the margin of error is from the middle to the outside, not left to right. So it means I have to I got to subtract and then divide by 2. So that's going to be 32.8 minus 27.1 divided by 2.
2.8,
What's that?
2.85.
2.85. Okay. By the way, that's a lot less than what they said. Okay. And what I've learned about Gallup, just a note, they often copy and paste their last one, their last article, and don't change it. So Gallup gets the 30% right. That one they do right, but often this margin of error is almost always wrong. It's usually bigger than what they said.
But in this case, it's smaller, right?
No, well, I'm sorry. Their margin of error is bigger than what it should be. That's what I meant.
Okay.
So they overestimate it, and it might be so it's like safety, so they don't get yelled at. Okay. So there's our margin of error. We could say, let's go here, with 95% confidence. We could say between 27.1% and 32.8% of all Americans, and I could say adult Americans, because 1-year-olds don't know if it's a good time to buy a house or not. Don't you agree? So I'm going to go for adult Americans. Okay, and then you just say what it is, and that is think that now is a good time to buy a house. Okay, and I want to highlight the word all. Because we're talking about the population proportion. And I will let you know, I will take off points if you do not in your statement say that you are talking about the population proportion. You could, and when you're talking proportions, you can either do with the word all, or you could have said the population proportion of all Americans who think that now is a good time to buy a house is between 0.271 and 0.328. That says that's the same thing, but you have to emphasize that it's population because that's different than the sample. Any questions on that? What is our what is our level of confidence for the sample proportion? It's
Is
the
it
hint.
still 95%?
No, the hint is it's really easy. It's 100%. We know the sample. Do you see? There's no question on the sample. They asked the people, and that's how many people said yes. Do you see that?
Oh,
Yeah.
that's why the word all is so important.
Exactly. Exactly. Because if you talk about the sample, then you don't have to get into confidence intervals. You just know the sample proportion. If you're talking about the population proportion, that is something that you never know exactly what it is. So you can only talk about confidence and intervals. Do you see that? Any questions on this? Any questions? Just let you know, sometimes when might you want to be 99.9% confident? Or maybe 99.99% confident?
Something with life and
Scientific
death.
calculation?
What's that?
I was thinking a scientific calculation.
Some, but what? Give me an example, for example.
Like a medicine, maybe? I don't know.
Yeah, especially medicine, where you're looking at a confidence interval where if you're wrong, you're going to kill people. Then 95% is not okay. I'm not okay with a 5% chance of killing someone. Are you? If maybe it's to, I don't know, to help them remove a little acne. Would you be okay with a 5% chance of killing someone by giving them acne medicine?
No.
No. So that would be where you want a much, much higher percent confidence level. Does that make sense? Okay, so sometimes you need a very high level of confidence. Okay, or if you're just reporting something out and if you're wrong, maybe you're going to get fired from your career job. That would suck, right? So then you want a higher level of confidence. Do you see how that works? So you want to think about what are the ramifications of being wrong. And if the ramifications are really bad, then go for 99 or 99.9. If the ramifications are not so bad, then 95%. And if the ramifications are like nothing, then you might want to go for 90%. Any questions on that? And I'm going to let you know in this class, we're going to stick to 90, 95, and 99 for your project. That way you can show me or understand what they mean. Does that make sense? And when I say your project, what am I talking about now? Which project?
2.
2.
Yeah, and guess what project 2 you're going to have to do?
Confidence intervals.
Confidence interval, but for something that we haven't learned yet. It's not this week. That's why I can't talk too much about it, but I can hint about it. Sound good?
Okay.
Any questions on the confidence interval for proportion? Okay. And by the way, if you want to interpret the confidence level, you would say that if many surveys were done of 1,018 people asking them if they think this is a good time to buy a house, and each of these will result in a different, maybe produces better confidence interval. So if I ask a different 1,018, I'm going to get a different interval. But I'm not going to have the exact number saying yes and no. Same number. So 95% of these intervals will contain the true population proportion of all adults, Americans, who think that now is a good time to buy a house. 5% won't. Any questions on that? Okay, now comes the next thing. So we have a sample size for the mean. So we had the central limit theorem, and that is sigma sub x bar equals sigma over root n. Do you remember that? I told you that was the big formula. Remember that?
Yep.
Okay, so what we want to do is we want to say, well, how big a sample size, okay, might you need? Maybe I'll even do our example. Okay, we had a sample size of 4, right? Our margin of error, if you look at it, it's up here. Was half this distance, right? And that was 1.3. Any questions on that? If you add or subtract 1 point, that's this number right here. What we subtracted and added was 1.3. Okay. Let's suppose we're not okay with 1.3. That's too big a spread. Let's suppose instead of 1.3, let's suppose we wanted, how about 0.5? We don't want to be off by more than a half a year. Because don't you think that'd be better numbers? We wanted to use it like to, help counselors in school to let them know when to talk to kids about getting passionate with each other. Does that make sense? And what age should they talk to kids, kind of thing. So let's suppose we wanted a 0.5 margin of error instead. Does that make sense?
Okay,
So how many people instead of 4 would we have to survey to make this work? Any questions on that? And the standard deviation was 1.291. And the idea, we can go up here. And our standard deviation, our sigma, is 1.291. And we want our margin of error to be 0.5. So what we do is we say, well, how are we going to get that 0.5 out of it? Now, that's not sigma sub x bar. That was, if you remember, the margin of error was how far you have to go from the mean. And that was, in this case, it was twice that. So it was about 1. So how big a sigma do you need? Okay, so the good news or bad news, depending who you talk to, is I created a calculator for this. By the way, when I say depending on who you talk to, who do I mean? Who do you think it's good that I have a calculator?
we do.
Students,
Yeah. Who do you think it's bad? Who do you think doesn't like it?
people that went to school for it for 4 years.
Yeah, in particular, some of my colleagues that want students to actually do the math. I got yelled at, sorry. But I never had a student be upset that I made a calculator for them. So my colleagues want them to do the algebra. So if you want to do the algebra, you can, but I'm not making you. So sigma, and it's our best estimate for sigma because we don't know exactly sigma, right? Sigma again was, I'm trying to remember again, was 1.291. That was our best estimate. We want our margin of error to be 0.5. And if we still want a 95% confidence level, then we need to survey 26 people, which is a lot more than 4, by the way. Any questions on that?
Is this essentially a power calculation?
Absolutely. Yeah, they call this, you've heard the word power before?
Well, I've used it before.
Okay, yeah, this is what's called power analysis.
Yeah.
So if we want to say 0.1 instead, then we'd have to survey 641 people. Any questions on that? To get that margin of error. Okay. And if you were okay with the 90%, we'd only have to survey 451 people. You see how it changes? Any questions on this? Okay, so the next one is we can talk about proportions instead. So I have 2 questions here. Okay, there's an A and a B, and we're going to do one at a time. Suppose you want to find a 99% confidence interval for the population proportion of cars in the United States that are electric vehicles. Okay, sounds like a good thing to find out, right? And if you want a margin of error of no more than 3%, how many cars must you look at? Any questions on the question? Okay, so I want to let you know there's actually 2 things going on. This question asks based on the margin of error in the confidence interval or the confidence level. This is different than what we did last week. What was last week was about?
Sampling distribution and standard error.
Yeah, but especially, remember you needed NP and NQ greater than 5?
Oh, yes.
That was a different sample size question. Is that clear?
Yes.
So that was even to do anything, basically. Here, this is to have kind of better results with smaller margin of error. Okay, so again, good news and bad news, or there's some people not happy and some people happy. The people happy are typically the students, not happy are a few of my colleagues. I made a calculator. So I'm going to go back to the calculator menu. And any guess on what number?
12. Is it? No.
13.
Yep, 13. Right. What's the big scary thing happening Friday?
Test?
No, we don't have a test on. I mean, you could take the test on Friday. Most people don't, though. It's Friday the 13th on Friday. So number 13. Yeah. So yeah, this Friday is your unlucky day if you're just decaphobia. Okay. So what I did is you have a choice. You can have an estimate for P, or you can have no estimate for P. Do we have an estimate for the proportion based on this question on part A?
No.
We don't. So this is a no estimate for P. Got it? So it's no estimate for P. Our margin of error was 3%. That's 0.03. And our confidence level was 99% or 0.99. And we need 1,844 in the survey. Any questions on that?
So does that mean you have to ask 1,844 people if they drive an electric car?
Yeah, or you have to, get on the road and take pictures of that many cars and see if they're electric or not. You choose. Sometimes you ask, sometimes you look. Does that make sense?
Yeah.
I zoned out. Can you explain no estimate for P one more time?
Oh, because we have no idea. I think it'll make more sense when I get to part B.
Okay.
So here's part B. You look at last year's data. 2.2% of all cars were electric vehicles. Okay. Now, how many cars would you need to look at for the 99% confidence interval? How is B different than A?
To give us estimate of P.
Yeah, now we have an estimate for P. Do you see that? Because our best guess is 2.2%. Is that clear?
Yeah.
So that's the no estimate versus estimate. So it helps to see them both. Otherwise, I think it's hard to know what's going on. Does that make sense?
Okay.
And in the real world, what you would do, just let you know, having an estimate for P is going to drop the sample size needed by a little bit, sometimes a lot. Got it? So if we have 2.2% as our estimate, so now I'm going to click have an estimate. And now it's 2.2% or 0.022, because that's 2.2%. Don't forget, when you're turning percents into decimals, you have to move the decimal over 2 places. And now if I calculate n, instead of 1844, what did I get?
That's a lot less.
It's a lot less. Okay. So in the real world, what you usually do is you do maybe, even if you had no clue, you do a survey of 100 or so. And then you use that as your estimate for P, find out how many more you need to survey, and then recalculate. Does that make sense? And that way you don't waste your time. Because if you really only needed 159, but we surveyed that 1,800, people, then we've really wasted time and money. Is that clear?
Okay.
Because you don't want to have to use a huge, large N if you don't have to, right? It's a lot of work or a lot of money. Any questions on this? I do want to emphasize that if you have a biased study, then is that going to change your N that you need?
Yeah, it would. By a lot, right? Because isn't
Yeah.
it exponentially?
No, the answer is no.
Really?
Yeah, and here's the reason. If you have a biased study and needed a small sample size, and you have and let's say I had a biased study and I had a large sample size, then we both have worthless data.
Oh,
You see, bias studies are worthless.
I got
So if you have a biased study, and especially a badly biased study, then it doesn't matter what your sample size is. Does that make sense? So for example, let's say you asked a whole lot of people how much they liked Donald Trump. But you were biased and all the people you asked were Republican. Do you think that is going to be a good estimate for the proportion of all Americans who like Donald Trump?
No.
It's gonna
That's
be
what I was.
terrible.
I was
And if you asked 1 million people, which is huge, it's still gonna be a terrible estimate. Do you see that?
yeah, like if you ask 159 people in San Francisco if they drive an electric car, it's going to be way different than if you ask 159 in, I don't know, Tennessee or something.
Right. And if you asked, say, 5,000 San Franciscos if they have an electric car,
Yeah.
and you use that for the proportion of America,
No way.
it's
It's going to be
still
way-
worthless. Do you see? It's
Yeah.
still worthless.
Yeah.
So a bias study is worthless. Got it? So everything we do needs chapter 1, which is preventing bias. Got it?
okay.
Okay. So that's just a note. And I want to, really highlight that because bias is bad. Got it? Sample size being large doesn't help. Okay. Sample size being large with unbiased studies helps a lot in making the margin of error smaller. You see how that works?
Yep.
Okay. So, and again, there is some mathematics involved in this, some really cool algebra and calculus, but I'm not getting into it. Sound good? But if you want, you can always come to Math Star. I'll torture you with the math. So 7:28, which means I always try to end around 7:30. And we have a secret word. And the secret word is population. How come?
Because all these confidence intervals deal with the population mean or proportion and not the sample.
Yeah, I like instead of deal with, they let you know of an interval at which the population is likely to be. Because they also deal with the sample, but the conclusion is about the population. Got it? Right? The conclusion is about the population. What you find is a sample, but your conclusion is about the population. Is that clear?
Yep.
So that's an important word because you must use the word population for mean. So let me show you. And let me highlight that in red, because if you don't write the word population mean, if you're doing a mean, what will happen?
You will be docked points.
Yep. Okay. And you either have to use population or like the word all, which is referring to the population when you're talking proportions, or you get dock points. So, don't get dock points. You don't want to lose points, right? So this is a promise that's really important to explain whether, talk about, are you talking about the population or you talk about the sample? And they're not the same things. Got it? Okay, so that's about all I have to say about confidence intervals. I'll let you know that, this gets deeper. We're going to talk about it again in a few weeks. But hopefully you understand they're really important. Do you get how important they are? It really gives you,
Just said, yep.
Yeah, it gives you a really good idea of not just what your estimate is, but how good your estimate is. What interval do you really think this population is in? Population mean or proportion? So I'm going to stop the share. And I'm even going to stop the recording.